Welcome to today's webinar. The topic today is modeling of parametric cross-sections in Rsection 1 and use in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the webinars, technical content of the website, etc. I will be the moderator today and I will answer your questions during the webinar. My colleague Sonja von Blow will be the presenter. She's responsible for the customer support and she's the main responsible person for the development of the add-on aluminium design and the standalone program Rsection that she will present today. Okay, I say something how you can ask questions. First, I switch off my webcam that you can see the full screen. Just click that button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Sonja. Sonja, it's your turn.
Thank you very much for the introductory words. I would also like to welcome you to today's webinar. The topic of this webinar is the modeling of cross-sections using parameters. You will learn how to import these cross-sections into RFEM. You will also be shown how to change the dimensions of the cross-section directly in RFEM using the parameters. It will be also explained how to enter tapered members with Rsection cross-sections in RFEM. Parameterized input allows model data to be entered in such a way that it depends on certain variables. These variables, such as length, width, or thickness, are called parameters. This allows you to create a series of cross-sections in different dimensions using just one cross-section. I would like to demonstrate this using the example of an angle cross-section. The leg lengths and thicknesses, as well as the angle between the legs, should be able to be defined variably. First, I model the angle cross-section and then I define the dimensions using parameters. I first create the short leg via the graphical input of a single element. I choose here the input mode, length and direction. The short leg has an angle of -30 degrees in work plane and a length of 80 millimeter and a thickness of 10 millimeter. The long leg has a length of 90 degrees in work plane, a length of 120 millimeter, and also a thickness of 10 millimeter. To make placement easier, I reverse the element orientation. Gaps have now appeared in the numbering. You can see this here in the table points. I eliminate these by automatically renumbering all objects. To do this, I first select the entire cross-section and then I choose Tools, Renumber Automatically. In this dialog, you have the possibility to influence the sequence of the numbering as well as the first number and the increment of the numbering. I click here on OK and the objects will be renumbered. I then dimension the cross-section. I use a linear dimension to dimension the long leg. To do this, I choose here linear and I assign also a symbol to this dimension. This should have the symbol H. Then I pick here my 2 points and then I create my dimension. I want to also dimension the short leg. This has the symbol B. I choose here the 2 points and create the dimension. Then I dimension the thickness T. I also want to dimension here the angle between the legs. For this, I use the angular dimension, and I want to also assign a symbol to this dimension. The symbol should be alpha. For the symbols, you can also use HTML commands. The character alpha is displayed with and alpha semicolon. Then I pick on the corresponding lines to create my dimension. Now the global parameters have to be defined. For this, I open the dialog via the button in the table. Each table row manages a parameter. It's necessary for the name of a parameter to consist of ASCII characters and to be entered without spaces. The name is used to address the parameter in the formulas. Each parameter name can only be assigned once. The unit group of the parameter must be selected from the list. This determines whether the parameter represents a length or an angle and so on. The definition type controls whether the parameter is described by a value or a formula. Depending on your selection, you can enter the value or the formula in the following columns. So if you choose the definition type value, I can enter the value directly here in this cell. If I choose the definition type formula, then I have to define the formula with which the value is then calculated. First, I create the parameter h for the long leg length. This is from unit group length, from definition type value, and the value should be 120 millimeter. I also create the parameter b for the short leg length. This is also from unit group length, definition type value, and the value should be 80 millimeters. I then create the parameter t for the thickness of the section, also from unit group length, definition type value is 10 millimeter. For the angle, I define the parameter alpha. HTML commands can also be used for the symbols. So I define here and alpha semicolon. The parameter alpha is from unit group angles, definition type value, and has the value 60 degrees. My global parameters are now complete, so I close this window with OK. The coordinates of the points can now be defined via the parameters. You have the option of addressing objects and their properties directly. For example, you can access the coordinates of points. This is useful if you want to define the coordinates of a point in relation to another point. You can call up a list of object properties using the info button in the console. To open the console, I go here to menu View, Console, and I click here on this info button. This opens the object property list. You can access the previously mentioned coordinates of a point via the object's property points, coordinate 1 for the y coordinate or coordinate 2 for the z coordinate. Here in the brackets, you have to enter the point number from which you want to take the coordinate. I don't want to use this property, so I click here on cancel. I set the parameter values so that they give the exact dimensions of the angle cross-section I just created. This gives me a way to check whether my functions are defined correctly. The y coordinate of point 1, this is this point here, is minus t divided by 2. You can enter this function directly into the table. Just type here equal minus t divided by 2. Alternatively, you can also enter the function using the Edit Formula button in the window. So I do this for the z coordinate. I open here the Edit Formula window and the z coordinate is minus h. And with OK, I have here now this formula assigned. After entering the formula, you will see the yellow triangle in the table cell indicating that the formula has been stored here. You can choose whether you want to display the values or the functions. To do this, just click here on this button, on this button, Show Formulas, to see whether the formulas or the values. The point 2 is defined by the functions in y direction equal minus t divided by 2 and 0. Point number 3 is 0 and minus h. Point 4 is here the 0 point, so I have nothing to do. And for the y coordinate of point 5, I open here the Edit Formula window. The y coordinate is described using the function t divided by 2 mal sine from 90 degree minus alpha. The formulas are interpreted in SI units. The corresponding SI unit for the angle is the radian. So I have to convert the 90 degree here. You can use the function degrees to radians to do this, which does this task for you. I will use this here. Degrees to radians. From 90 degree. The parameter alpha here is automatically used in the correct unit, so it does not have to be converted. So then I click here on OK. I copy the remaining formulas from a prepared file. So I will do this here. The point coordinates are now all defined using parameters. Now only the thickness needs to be defined using the parameter t. I define this using the elements table, and here I define for each element the parameter t. The cross-section is now completely defined by parameters. By changing the values in the global parameters, you can now adjust the dimensions of the cross-section and thus create any cross-section in the series. To demonstrate this, I open the global parameters and I change here the parameters. For example, for H to 180 millimeter, also for B, C should be 5 millimeter, and alpha should be 30 degree. If I click on OK, the cross-section will be modified. You can use the created cross-section in RFEM. To do this, I first save the cross-section in Rsection, and then I switch to RFEM. I have already created a file here. You can now import the cross-section you have just created. I import the section via Navigator Data, New Section. I open the section library from Rsection. I choose here this cross-section and I click on OK. The global parameters of the cross-section defined in Rsection are now listed in the Global Parameters tab. You have the option of adjusting the values of the parameters. I will do this. I change here the parameter H to 120 millimeter, B to 80 millimeter, T to 10 millimeter, and alpha to 60 degree. You can also create tapered members using the Rsection cross-section. The initial cross-section should be the section I just created here. The final cross-section should have a larger leg height of 180 millimeter than the initial cross-section. To do this, I copy the Rsection cross-section, and then I just change here the length of this parameter to 180 millimeter. I now create a new single member. In the Section tab, I choose here the distribution type linear. And for the member start, I select my first cross-section. For the member end, I select my second cross-section. Then I create my cross-section. You can then check the correct modeling and the rendering. The cross-section could only be interpolated if the cross-section change is displayed as a linear distribution. This is the case here. Only in this case, a design in the design add-ons is possible. It is important to note that the angle difference between the cross-section parts must not be greater than 0.1 radians. This means 5.7 degrees for both R-section cross-sections and database cross-sections. To demonstrate this, I will change the angle of the final cross-section to 90 degrees. So I will do this. I change here this global parameter to 90 degrees. And now the angle difference is greater than 0.1 radians. So if I click on OK, the rendering will no longer show a linear distribution, and the design in the design add-ons would not be possible for this member. The reason is that you want to avoid cross-section parts that are not flat. To illustrate this, I have created such a member as a surface model. I will open this here. The cross-sections have the dimensions 120 millimeter and 80 millimeter. However, the initial cross-section has an angle of 90 degrees and the final cross-section has an angle of 30 degrees. This means the angle difference is 60 degrees, and this is greater than this 5.7 degrees. The surface of the short leg, you can see this here, is now no longer flat. You can also create tapered members with R-section cross-sections that are not defined by parameters. When modeling, it's important to note that the final cross-section must be a copy of the initial cross-section, and that no geometric objects such as points or elements may be added or deleted. I would like to show this with an example. For this, I switch to R-section again. First, I create the initial cross-section. To do this, I create a new file. It's my start cross-section. Analysis method is thin wall analysis. The initial cross-section is an angle cross-section with the dimension h 120 millimeter, thickness 10 millimeter, and for the other dimension it's 80 millimeter and also 10 millimeter. Then I save this cross-section. I then create the final cross-section from the copy of the initial cross-section. To this, I go here to File, Save As, and I enter here End, click on Save, and then I change the dimension H to 180 millimeter. To do this, I select here these nodes, and then I choose Move Copy Selected Objects, and then I move these objects by minus 60 millimeters in a set direction. Then I save this file. I switch to RFEM again. I go to my first example. and then I import these two cross sections. So I go here to new section, section library from our section. Then I choose here start and end, click on OK. Then I have here my two cross sections, and then I will enter a new member with distribution type linear. Member start is my start cross section, member end my end cross section, and then I create here this cross section. The rendering shows a linear distribution, so the modeling is correct. This brings me to the end of the webinar. I will now hand the floor back to Andreas.
Thank you, Sonja, for your presentation. I have an additional hint for you. You can book our online courses, for example, the RFEM 6 Masterclass course. It's a course for beginners, or the Eurocode 2 or Eurocode 3 courses. You can get more information and prices when you scan the QR codes, or you can press that buttons with the links at the bottom. Now you can download the slides from the website. In the next days, you will get an email with your certificate, with the link to the recording models, and these slides. Okay, that should be also all from my side. I thank you for your attention. Thank you, Sonja, for your presentation. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.